Hi, this is Charles Maggio. Welcome back to R for Epidemiology. In this screencast, I want to introduce logistic regression modeling in R. And it is a big topic, and it's hard to do it in 10 or 15 minutes, so we're going to move very quickly. Before we actually get into the coding in R, which is really somewhat straightforward and relatively trivial, I do want to spend at least a couple of minutes talking about what logistic regression modeling is, what odds are, what log odds are. Okay, the first thing is the idea of odds, and odds are odd things, if you pardon the pun. But basically, odds are a way for epidemiologists to approximate risk ratios and get around some of the limitations of working with probabilities. And we need to talk a little bit about that. So an odd itself is basically the ratio of two probabilities. So there's a probability and then one minus that probability. That basically is what an odd is. That being said, when we start talking about odds and using an odd and odds ratios and log odds and logits, things can get very confusing relatively quickly because human beings are not really in the habit of thinking in terms of odds. So generally, you'll think of odds as an approximation of a probability or a risk of some time, but it's just slightly skewed off. So let's talk about the odds of a day, of a random day in the week being a Sunday. And the odds of one day of Sunday are, in fact, 6 to 1 against. Now, what do we mean by that? Well, we have to really evaluate that and think about that in terms of the way I think human beings are more normally used to thinking about an event occurring, or not an event, or event not occurring. So really, the probability of a Sunday is in fact 1 over 7. So how do we get 6 to 1 against to mean something to us in terms of 1 to 7? Well, there's a few different ways. So one way you could think about it is that in 7 trials, we fail 6 times, and we succeed, if you will, 1 time. And that's sort of how you get that 6 to 1 ratio. Or you could think that it's 6 times more likely to be a day other than Sunday, right? Or on the opposite side, we could look in terms of what we can call decimal odds. And a decimal odd is essentially like 1 over 6, which in this case works out to be about 0.166, right? And the decimal odds of a day being a Sunday out of 7 days is actually 1/6. Now compare this actually to the probability, which is equal to 1/7, which I've worked out already actually, and is 0.143. Just a little bit different, this from this, is it not? Have to kind of keep that in mind, and it does play into sort of our approximation of relative risks from odds ratios. This whole idea of odds is really a little strange. It really arises from betting and from gambling, and the reason why it kind of makes sense in betting and gambling. Let's take this decimal odds. If you have a decimal odd of 1/6, which we said was 0.166 or about 0.17, you could think of a decimal odd as a stake. And a stake is how much you need to bet to get $1, basically, to get something. And here you would say you would bet 17 cents to win $1. In this case, 17 cents is your stake against the dollar. But that's neither here nor there. That's not really what we use it for in epidemiology. It's just a way to sort of set the case. Really, we like odds in epidemiology because they are not bounded by 1. Probabilities have to be bounded by 0 and 1, right? Odds in and of themselves can go from 0 to infinity. Then we take the next step, which is to take the log of the odds, which extends it even farther. Just to orient ourselves, if the probability of A equals the probability of B, then we say that the odds are equal to 1. Right? It's 1 to 1 against. The logit, or the log of the odds, in this case, would be equal to 0. And that sort of like orients us a little bit. So we take that one step further and start talking about the logistic model. And the logistic model is part of the generalized linear model. And a generalized linear model basically is something that we use in statistics when the response variable is not expected to be normally distributed. And what we do is we have a link function, and in a GLM, we have basically y is some sort of function of x. So it's a function that changes the response variable, so that we could apply some of our regression tools to it. In the logistic regression, the logistic function actually is this somewhat odd thing that includes odds, but basically is the exponentiation of a regression formula. So I'm trying, let's say, b0 plus b1 over 1 plus that same expression plus b1. And this is equal to the logistic function. The next step up actually is a logistic transformation, which really involves a couple of different transformations. When we do the logistic transformation, we end up taking the logit of that logistic function, and we end up really with the logit of y being that regression formula that linear regression formula that we're really trying to get at in the first place. So what we do then is we basically we start really with probabilities, and then we convert those probabilities to odds, so that the values range from 0 to infinity, and then we take the odd, then we take the log of the odds. And we're going to walk through this very quickly. But in the end, after we've done all that, we end up with a logistic regression where the logistic regression formula where the logit transform proportion of the probability of an outcome, the linear is a linear regression on the logit transformed proportion or probability of an outcome at each value of the predictor. A lot of words. Most folks at this point, probably the point you're at in your epidemiologic career, understand what that kind of means anyway, and you have an intuitive sense. We end up just sort of like exponentiating the log odds and end up getting the odds ratio. But let's take a quick look at what we're really talking about, and I think it makes the most sense if you actually walk through this logistic transformation. So we start off with probabilities. We're going to start off with a sequence of 21 probabilities that range from 0 to 1. And these are just probabilities. The probability of an event occurring. Someone being sick, not being sick. Someone being admitted to the hospital, not being admitted to the hospital. What we want to do then is we take the first step in the logistic transformation, which is to convert these probabilities to odds. And in R, it's extraordinarily simple. It's just the probability, which we just created a vector of probabilities, divided by 1 minus the probability, which we do with this little formula, and we're going to save it as another vector called odds. Run that. Now, notice one little thing here, right? Okay, we have probability of 1 over here, right? And the odds of a probability of 1, or 1 over 1 minus 1, is dividing by 0, and we get infinity. So we could always index that out if we really wanted to. It's kind of easy to do. You just index out that observation right there. But we really don't have to in this example. We're just going to keep it the way it is. The next step, the second step then, is to take the log of these odds, which is the second step in this transformation. And we do that, and here now we end up with infinity at both ends, which is really what we were trying to get at. We were trying to get this. We were trying to extend the line and get beyond the limits of 0 and 1, which are basically constraining us if we're using straightforward probabilities. Easiest to see it if we just simply plot these things. So we created those probabilities, and they are simply a straight line, a linear set of probabilities, which we created as a sequence of probabilities bounded from 0 here to 1. The index just refers to the number. If we plot the odds that we created from those probabilities, this is what we see. Now we are still bounded at 0, but now the positive bound has increased to infinity, as we saw. Now, if we plot the logit of those odds, the log of those odds, we see the logistic transformation, which in this case is slightly sigmoid in shape, but this basically is where we want to get to. Interesting point about this. The logistic transformation actually is most accurate near the center. We're closest to linear. It starts to go off a little bit. There are, some certain approximations. If you read Gellman and Hill, they talk about approximations you could use to interpret the results of logistic regression, and they're really straightforward sort of rules of thumb that work nicely in here, but don't work as nicely out here. But this is what we're trying to get at. So now, let's take a quick look at an actual example of a logistic regression. After all this preamble, an actual logistic regression is relatively straightforward. I'm going to start off by going to this lovely UCLA site that has a lot of wonderful examples on using a few different statistical programs, Stata, SAS, R. In this case, we're going to download a data set, a CSV, a comma separated value data set that they have that is some data. I'm not sure if it's real or not on admissions, but we could take a quick look at it. So let's run. So we're going to save it as an object called admissions. It basically is a data set that looks at admission as a 0, 1, a binary outcome variable that can be explained possibly by someone's GRE score or someone's grade point average, and perhaps by the rank of the institution from which they graduated during their undergraduate career. So the logistic model we are interested in running then is whether admission, this 0, 1 dichotomous outcome variable, is a function of GRE, GPA, and perhaps controlling for or using as an explanatory variable the rank of the school. Notice here that the rank of the school is an integer variable, and we are explicitly reading it in as a factor variable because we're going to want to compare the different schools ranking from 1 to 4. The only difference between a linear model and this generalized linear model here is we put a little g in front of the LM. It's now a generalized linear model. And we specify the kind of log link, the kind of link we want, or the type of family from which we want to choose the regression. In this case, it's a binomial family with a logistic transformation. And we have the formula here, and we specify the data just as we did with linear modeling. Run this model and save it to an object called admit.model1. Let's run that. And now we have our model. In much the same way that we explored our linear models, we can get a summary of the logistic model, and here we do. And we see the model call itself. Now, instead of residuals, we get deviance because we can't calculate residuals in a logistic framework. We see the different estimates, the different coefficients for each of the variables we're interested in. We see that they all are statistically significant. If we really wanted to interpret them, and why run the model if we didn't want to interpret them? Here's one way you can get at it. This is the intercept. Remember, this is on the log odds scale. So the sort of like straightforward and somewhat relatively naive way of looking at it is saying, okay, for every 0.02 increase in GRE, there is a 1 point increase. For every 1 point increase in GRE, there is a 0.02 increase in the log odds of admission. And then we always say holding the other variables constant. And what do we really mean by that? Well, in this case, what we really mean is if someone has a GPA of 0, and if someone actually graduates from the lowest ranked school, which is the rank 1, I believe. Rank 4 would be the lowest ranked school. Does that really mean anything? We have to think about them. Again, you need to take from your classwork and your experience running regression models how important it is to interpret coefficients in terms of what we mean in terms of these multiple regressions. You may want to mean center something. You may want to manipulate the data originally so they might make more sense in terms of interpreting these coefficients. But in any event, here let's just say that it makes sense to say that for every 1 unit increase in GPA, there is a 0.80 increase in the log odds of being admitted. As far as interpreting these coefficients for the factor level variables, these are each compared. Notice that they rank. Basically, there's 2, 3, and 4. So basically, compared to a first ranked school There is, comparing a first rank school to a second rank school, there is a log odds decrease of minus 0.67, or a log odds decrease of minus 1.34. What do we mean by log odds? I mean, it's hard enough to interpret odds and odds ratios. It's really difficult to interpret log odds. So what we will generally do is we will exponentiate them. Just to show you here, the exponentiation is just simply the exponentiation function, and we're binding the two results we want. We want the coefficients and we want the confidence interval, and we can extract them from our model using the coefficient and the confidence interval functions that work on regression models. Just to show you what that one looks like. Here, for example, if you just use confidence interval, you will get the confidence interval on the log odds scale. But we want to exponentiate that, so we run that. In this little snippet of code here will return the results we really want. Now, as epidemiologists, we're happy. We're working in the odds ratio scale. So now we could say, oh, so if you graduate from a second rank school, you're half as likely to be admitted to whatever school this admission did. I mean, it might be admission to UCLA. I'm not entirely sure, but you're half as likely here, right? If you rank from a third rank school, if you graduate from a third rank school, you're essentially 74% less likely, or here 79% less likely. Here you are twice as, for each 1 unit increase in your GPA, you are about twice as likely to be admitted. For every 1 unit increase in your GRE, you are, what is it, 0.002 increased probability or odds ratio or likelihood. In any event, that is logistic regression in R. It's relatively straightforward to run. It's relatively straightforward to extract the kinds of information that you need from it, simply using the summary function and the confidence interval function with the coefficient function and the exponentiation function. You could use all the other regression functions we've spoken about in terms of updating and plotting. You'll get the same. You'll get some very nice results from this. And the go-to function to do this kind of work is the GLM function.